Okay, let's make a program where we can find the exact probability of getting at least 10 sixes when you roll a die 20 times. So this is not a simulation, we're actually going through this. So let's, first of all, we're going to be, because you guys created a program that computes combinations and permutations, now we're going to use one of Mathematica's programs, Binomial, which just computes combinations. So if I wanted to say, like, there are 4 things and I'm choosing 2 of them, Binomial, you put in how many things that you're choosing, how many things you're choosing from and how many things you're choosing, and Binomial calculates it where order doesn't matter. So if I press Shift Enter, that gives me 6. But there are 6 different ways to arrange it, and that should make sense. All right, well, what if instead I said, there are 20 things and I'm choosing 10 of them? What this would find is the number of ways in which I could have 20 rolls and get 10 sixes. And then I'm going to multiply that. Well, there are 10 other rolls, and in those 10 rolls, there are 5 different face values, 1, 2, 3, 4, and 5, that are not sixes. So 5 raised to the, well, to the 10. So this will give me the total number of ways in which I can get 10 sixes, and then I want to divide that by all the number of ways in which I can roll 20 die, so 6 raised to the 20th. So this will give me, this is the probability that I get 10 sixes. But I want to find the probability that I get at least 10 sixes. So what I'm going to do is I'm going to create a probability count variable. And I'm going to start it at 0. And then I'm going to start a while loop. So while, well, what I'm going to do is I'm going to take, I'm starting it with 10 sixes, so I'm going to say r equals 10. And as long as my r value is less than or equal to 20, so this is going to say I'm going to start at 10 sixes, and I'm going to go up to getting 20 sixes. So I'm going to calculate the probability of getting 10 sixes, the probability of getting 11, the probability of getting 12, and add them all together. So while the number of sixes that I want is less than or equal to 20, and it's starting at 10 because I want to get at least 10, I'm going to do this binomial distribution. But instead of putting 10 here, I'm going to say that we're doing 20 to r, because that r value is going to keep going up. So when, like, if the r value was 13, it would be there are 20 die and I want 13 rolls. And this value here, this 10, is like getting everything that isn't a 6. So if I'm getting r sixes, I'm going to want 20 minus r is how many non-sixes that I get. So again, our r value is talking about the number of sixes. And okay, so as long as the number of sixes is less than or equal to 20, I'm going to do this new count, and this is going to be my probability count. So my probability counts at 0, and this expression will count the probability for having 10 or 11 or 12 or 13, however many sixes. So I just want to be adding these probabilities together. So I'm going to add this to whatever my probability count was before. And then all I'm going to do now is do r++. And that's it. So I may want to make this look a little bit prettier, so I could say print well, I'll print the probability of getting at least 10 sixes on a roll of 20 is, and then I'm going to enter my probability count. And let's see how this works. So I made a simulation earlier that predicted it to be 1 out of 2,500. So let's just see how close those are. I could do 1 out of 2,500, which was what I got when I made a simulation, and divide it by my probability count. And if my simulation and my actual calculation are actually working, this value should be close to 1. And it's not perfect, but it is fairly close. So if I wanted to do this, if I wanted this to be a lot better in my simulation, I would have to do my simulation a lot more times. Okay, that's it.